For the last 2 centuries, the entire modern world has been powered by a single hidden mechanism. Whether it's a coal plant from the 1800s or a cutting-edge nuclear reactor today, if you trace the power cables back to their source, you will almost always find a giant metal turbine spinning inside a massive building. Despite the incredible complexity of the fuels we use, the core job of those plants is simple. They boil water. They generate heat, turn water into steam, and use the pressure to push those turbine blades. Those giant clouds of vapor you see rising from power plants are the physical byproduct of the Rankine cycle, the thermodynamic engine of modern civilization. But that cycle has reached its physical limit. At the end of 2025, engineers in China connected a new kind of power plant to the grid that doesn't use water at all. They commercialized a technology that researchers have been attempting to build for decades, replacing steam entirely. To see why replacing steam is a priority for every major industrial power, we need to look at the invisible physical bottleneck that has capped energy efficiency for generations. Water requires massive energy to force it into a gas. Heat is consumed breaking the molecular bonds to create steam. Because of this phase change penalty, average thermal plants top out around 33% efficiency, losing most fuel as waste heat. Furthermore, steam is a low-density gas. To capture enough kinetic energy to power a city, you must push a massive volume through the system. This requires enormous pipes, massive cooling towers, and hangar-sized turbine halls. As global energy demands accelerate, relying on sprawling facilities that lose the majority of their thermal energy is becoming untenable. The infrastructure of the future cannot be built on machines the size of warehouses that vent most of their potential into the atmosphere. This is the mountainous region of Guizhou, China. Deep inside a steel plant here, a project called Chaotan 1 recently began feeding electricity into the grid. It is the world's first commercial supercritical carbon dioxide power generator, and its operation follows 17 years of research into a very specific state of matter. This graph shows the phase states of carbon dioxide. When you compress CO2 to 73 times normal atmospheric pressure and heat it past 31 degrees Celsius, it crosses a threshold. It stops being a standard gas or a liquid and enters what is known as a supercritical state. In this state, the CO2 exhibits a combination of properties. It becomes incredibly dense, packing in tightly like liquid water, which allows it to store and carry a massive amount of energy. But at the same time, its viscosity remains low, meaning it flows through pipes and turbines with the minimal friction of a gas. Because supercritical CO2 is so dense, you can push the same amount of mass through a much smaller machine. A turbine generating 10 megawatts of power with steam requires heavy, sprawling machinery. A supercritical CO2 turbine producing that same 10 megawatts is compact enough to fit on a small workbench. By eliminating water, engineers bypass the energy penalty of the boiling phase change. The fluid stays in a closed loop, taking in heat and spinning the turbine at efficiencies that can reach 50%, an increase that is physically impossible for steam-based systems. This efficiency leap is arriving at a critical moment for industrial growth. By 2030, the energy required to run data centers for artificial intelligence is projected to jump by 165% in the United States alone. Expanding traditional steam-based infrastructure to meet this demand is difficult. Those plants require vast amounts of real estate and millions of gallons of fresh cooling water, resources that are increasingly limited in the regions where these data centers are built. Because supercritical CO2 systems operate in a closed, water-free loop, they can be deployed in arid environments or space-constrained urban centers. They are also effective at scavenging waste heat from existing industrial sites, like the steel mill in Guizhou, and converting that exhaust directly into electricity. At the Chaotan 1 facility, the system captures medium-temperature exhaust from the sintering process. That captured heat alone allows the plant to generate over 70 million kilowatt-hours of electricity a year, providing roughly 30 million yuan in new annual revenue. Moving from 33% to 50% efficiency provides the physical capacity needed to sustain the high-power demands of the AI economy without relying on new water resources. The math behind this technology isn't new. The theoretical physics of supercritical CO2 power cycles were first proposed in 1948, but actually building a machine that could withstand these conditions remained a major engineering challenge for over 70 years. Researchers faced several hurdles that stalled the technology for decades. At 600 degrees Celsius and extreme pressure, supercritical CO2 is highly corrosive to standard metals. Furthermore, preventing the dense gas from leaking out around the rapidly spinning turbine shafts required seals that didn't exist until very recently. The U.S. STEP program has focused on long-term testing to ensure the reliability of these components by the 2030s. Meanwhile, the Chinese team at the Nuclear Power Institute developed domestic capabilities in vacuum diffusion welding and high-temperature dry gas seals to push a commercial-scale unit onto the grid ahead of that schedule. By commercializing the technology first, a nation gains real-world data on maintenance and degradation, creating a significant advantage in manufacturing the components for future thermal energy projects. Some industrial analysts remain cautious. Building a pilot generator is a major step, but keeping it running is another. The true test of Chowtown 1 is whether its high-tech alloys and microchannel heat exchangers can survive 5 years of continuous industrial wear and tear without excessive maintenance costs. If the machinery proves reliable, the effects will be widespread. It would enable power grids to operate independently of fresh water supplies and allow for the development of much smaller, hyper-efficient nuclear reactors that operate at temperatures currently too high for steam turbines to handle. Proving these supercritical cycles at scale changes the logic of where a nation can build its industrial base. By owning the manufacturing standards for these compact turbines, a country can export the infrastructure needed for high-density power in a world where water and space are increasingly at a premium. The steam engine provided the baseline for 2 centuries of growth, but it is reaching its physical limit. As artificial intelligence drives power demands past what traditional grids can support, the move toward higher density energy represents the next major shift in how industrial nations will compete. To see how these energy breakthroughs are impacting the global economy, subscribe and watch our next video.